which greatly simplifies the world for us application developers who sit on top of it. Networking layers. In networks, each layer builds on the abstractions of the previous one. This way, when you're requesting a web page, you don't need to know which voltages represent a 1 or a 0 on the network wire. You just need to know how to use the next layer down the stack. While the full networking stack is fascinating, there are 3 key layers that come up most often in system design interviews. Network layer. Layer 3. At this layer is IP, the protocol that handles routing and addressing. It's responsible for breaking the data into packets, handling packet forwarding between networks, and providing best effort delivery to any destination IP address on the network. However, there are no guarantees. Packets can get lost, duplicated, or reordered along the way. Transport layer, layer 4. At this layer, we have TCP and UDP, which provide end-to-end communication services. TCP is a connection-oriented protocol. Before you can send data, you need to establish a connection with the other side. Once the connection is established, it ensures that the data is delivered correctly and in order. This is a great guarantee to have, but it also means that TCP connections take time to establish, resources to maintain, and bandwidth to use. UDP is a connectionless protocol. You can send data to any other IP address on the network without any prior setup. It does not ensure that the data is delivered correctly or in order. Spray and pray. Application layer. Layer 7. At the final layer are the application protocols like DNS, HTTP, WebSockets, WebRTC. These are common protocols that build on top of TCP to provide a layer of abstraction for different types of data, typically associated with web applications. We'll get into them in a bit. These layers work together to enable all our network communications. To see how they interact in practice, let's walk through a concrete example of how a simple web request works. Request lifecycle. When you type the URL into your browser, several layers of networking protocols spring into action. Let's break down how these layers work together to retrieve a simple web page over HTTP. First, we use DNS to convert a human-readable domain name like hellointerview.com into an IP address like 324.252.62. Then, a series of carefully orchestrated steps begins. DNS resolution. The client starts by resolving the domain name of the website to an IP address using DNS, the domain name system. TCP handshake. The client initiates the TCP connection with the server using a three-way handshake. The client sends a synchronized packet to the server to request a connection. The server responds with a synchronized acknowledge packet to acknowledge the request. The client sends an acknowledge packet to establish the connection. Request. Once the TCP connection is established, the client sends an HTTP GET request to the server to request the web page. Server processing. The server processes the request, retrieves the requested web page, and prepares an HTTP response. HTTP response. The server sends the HTTP response back to the client, which includes the requested web page content. After the data transfer is complete, the client and server close the TCP connection using a four-way handshake. The client sends a finish packet to the server to terminate the connection. The server acknowledges the FIN packet with an ACC. While the specific details of TCP handshake might seem technical, 2 key points are particularly relevant for system design interviews. First, each round trip between client and server adds latency to our request, including those to establish connections before we send our application data. Second, the TCP connection itself represents state that the client and server must maintain. Unless we use features like HTTP provide, we need to repeat this connection setup process for every potentially significant. Understanding when connections are established and how they are managed is crucial to touching on the important choices relevant to recent updates. It's less common recently in big tech, but it used to be a popular interview question to ask candidates to dive into the details of what happens when you type hellointerview.com into your browser and press enter. Details like these aren't typically a part of a system design interview, but it's helpful to understand the basics of networking. It may save you some headaches on the job. The L4 load balancers. Layer 4 load balancers operate at the transport layer, TCP/UDP. They make routing decisions based on network information like IP addresses and ports, without looking at the actual content of the packets. The effect of an L4 load balancer is as if you randomly selected a backend server and assumed that TCP connections were established directly between the client and that server. This mental model is not far off. Key characteristics of L4 load balancers. Maintain persistent TCP connections between client and server. Fast and efficient due to minimal packet inspection. Do not make routing decisions based on application data. Typically used when raw performance is the priority. For example, if a client establishes a TCP connection through an L4 load balancer, that same server will handle all subsequent requests within that TCP session. This makes L4 load balancers particularly well suited for protocols that require persistent connections, like WebSocket connections. At a conceptual level, it's as if you have a direct TCP connection between client and server, which we can use to communicate at higher layers. Layer 7, load balancers. Layer 7 load balancers operate from the application layer, understanding protocols like HTTP. They can examine the actual content of each request and make more intelligent routing decisions. Key characteristics of L7 load balancers. Terminate incoming connections to create new preserve your mental energy and inner time for the parts of the system that truly matter. Disadvantages. Higher latency than other methods. Updates might be delayed as long as the polling interval plus the time it takes to process the request. Limited update frequency. More bandwidth usage. Can be resource intensive with many clients, establishing new connections, and so on. When to use simple polling. Simple polling is a great baseline, and unless you specifically require very low latency, real-time updates is a great solution. It's also appropriate when the window where you need updates is short, like in our late code system design. Things to discuss in your interview. You'll want to be clear with your interviewer about the trade-offs you're making in polling versus other methods. A good explanation highlights the simplicity of the approach and gives yourself a back door when you discover that you need something more sophisticated. I'm going to start with a simple polling approach so I can focus on X, but we can switch to something more sophisticated if we need to later. The most common objection from interviewers to polling is either that it's too slow or that it's not efficient. Be prepared to discuss why the polling frequency you've chosen is appropriate and sufficient for the problem. On the efficiency front, it's great to be able to discuss how you can reduce the overhead. One way to do this is to take advantage of HTTP Keep Alive connections. Setting an HTTP Keep Alive which is longer than the polling interval will mean that, in most cases, you'll only need to establish a TCP connection once, which minimizes some of the setup and teardown overhead. Long polling, the easy solution. After a baseline for simple polling, long polling is the easiest approach to achieving near real-time updates. It builds on standard HTTP, making it easy to implement and scale. The idea is also simple. The client makes a request to the server, and the server holds the request open until new data is available. It's as if the server is just taking really long to process a request. The server then responds with the data, finalizes the HTTP requests, and the client immediately makes a new HTTP request. This repeats until the server has new data to send. If no data has come through in a long while, we might even return an empty response to the client so that they can make another request. For our chat app, we would keep making a request to get the next message. If there was no message to retrieve, the server would just hold the request open until a new message is sent before responding to us. After we receive that message, we make a new request for the next message. Client makes HTTP request to server. Server holds request open until new data is available. Server responds with data. Client immediately makes a new request. Process repeats. The code shown here demonstrates the client side of long polling, where a loop continuously fetches updates from the server, processes the data, and retries with a small delay or error. The simplicity of the approach hides an important trade-off for high-frequency updates. Since the client needs to call back to the server after each receipt, the approach can introduce some extra latency. Assume the latency between the client and the server is 100 milliseconds. If we have two updates which occur within 10 milliseconds from each other, with long polling we receive the first update 100 milliseconds after it occurred, 100 milliseconds without latency. But the second update may be up to 290 milliseconds after it occurred, 90 milliseconds from the first response to finish returning, 100 milliseconds from the second request to be made, and another 100 milliseconds to make a response. Advantages. Built on standard HTTP, it works everywhere HTTP works. Easy to implement. No special infrastructure needed. Stateless server side. Disadvantages. Higher latency than alternatives. More HTTP overhead. Can be resource intensive with many clients. Not suitable for frequent updates due to the issues mentioned above. Makes monitoring more painful since requests can hang around for a long time. Browsers limit the number of concurrent connections per domain, meaning you may only be able to have a few long polling connections per domain. When to use long polling. Long polling is a great solution for near real-time updates with a simple implementation. It's a good choice with updates are infrequent, and a simple solution is preferred. If the latency trade-off of a simple polling solution is at all an issue, long extension on log pool that allows the server to send a stream of data to the client. Normally, HTTP responses have a header like a content line, which tells the client how much data to accept. SLC instead uses a special transfer method chunked, which tells the client that the response is a series of chunks. We don't know how many there are or how big they are until we send them. This allows us to move from a single atomic request response to a more granular stream apps, or anything else in there. Think of WebSockets like a TCP connection with some niceties that make establishing the connection easier, especially for browsers. Light initiates WebSocket handshake for each connection upgrades to WebSocket protocol. Both client and server can send messages. The connection stays open until explicitly closed. For our chat app, we connect to a WebSocket endpoint over HTTP, sharing our authentication tools via cookies. The connection would get upgraded to a WebSocket connection, and then you'd be able to receive messages back to the client over the connection as they happen. Bonus, we'd also be able to send messages to other users in the chat room. The code shown here demonstrates both the client side, which opens a WebSocket connection, handles incoming messages, and implements reconnection logic on close, and the server side, which listens for connections, processes incoming messages, and sends updates to clients when data changes. Extra challenges. Because the WebSocket is a persistent connection, we need our infrastructure to support it. Some L7 load balancers support WebSockets, but support is generally spotty. Remember that L7 load balancers aren't guaranteeing we're using the same TCP connection for each incoming request. L4 load balancers will support WebSockets natively since the same TCP connection is used for each request. When we have long-running connections, we have another problem: deployments. When servers are redeployed, we either need to sever all old connections and have them reconnect, or have the new servers take over and keep the connections alive. Generally speaking, you should prefer the former.